Hello everyone, welcome to Mind Maps. In this video lecture, we are discussing homotopic, enantiotopic and diastereotopic groups and atoms. So it's kind of all in one situation. So let's start. What are homotopic groups? Homotopic groups cannot be distinguished by any means whatsoever. They are chemically entirely identical. Okay. So we'll see what this means. It has to be the simplest explanation that we can see. They are like identical twins or something like that कह सकते हैं. तो पहला example देखते हैं. See the first example. You can see the two hydrogens, hydrogen 1 and hydrogen 2. We decide whether atoms are homotopic or not. So these two hydrogens are equivalent. Okay, you can substitute anyone and the result is almost the same. Okay, so you see dichloromethane. Both these hydrogens are homotopic. Okay, so when you substitute any one H by D, okay, and when you superimpose, so they are identical. Okay, so what we see is H and H are homotopic and both the chlorine atoms are homotopic. Now when an axis of symmetry is present, C2 axis of symmetry is present, okay, these both the molecules have two chiral centers and there is no plane of symmetry. Okay, but the hydrogens are homotopic because of C2 axis of symmetry, because once you rotate this, जब C2 को rotate C2 axis के along इस molecule को rotate किया जाएगा, okay, तो इनकी hydrogens की जो position है that gets interchange हो जाती है, ठीक है, that gets interchange. So that's how why these are homotopic. Now this is the first criteria that we are deciding on. Okay, we'll just look through the examples. So it can be broadly divided into substitution and the C2 axis that we discussed in the previous slide. ठीक है, अब ये देखो, ये एलीन आपको दिख रहा है, एलीन. ओके, यहाँ पे HA और HB है, HA and HB. okay, you can substitute any one atom by X, okay, and then you will have these two molecules which are basically the same. Okay, if we don't know allenes, they are not in the same plane. Okay, these two are in different planes. The hydrogens on the left hand side and hydrogens on the right hand side, both are in different plane perpendicular to each other. Okay, so but these compounds are basically same, identical products, so these atoms are homotopic. Now as you can see, this is acetone in example number 5. okay, as you see here, okay, in case of acetone, this is not okay, so these are maybe two groups present above the plane and below the plane, and we have a carbonyl group. So when there is an attack from the top face, we get a product, and when there is an attack from the bottom face, there is another product. Okay, this is how we see. So when you substitute from the, say, top face, the hydrogen in red, we get a product like this. Okay, and actually this is an addition reaction, and the hydrogen from the down face, we get another product. So these are basically the same. Okay, these are same, these are not stereoisomers, but the product is same, so these are homotopic faces. Okay, now the second criteria is rotation. What happens in rotation? We have a C2 axis. Okay, C2 axis, when you rotate the molecule by 180 degrees, okay, so the position of the hydrogens interchange, HA, HB. okay, when you rotate it by 180 degree along C2 axis, there is HB and HA. So basically the hydrogens remain the same, there is no change in molecule as in journal. Okay, So what you see is you can interchange the position of hydrogens, right? So when we have a homotopic group, we have only one NMR peak, okay? NMR spectroscopy, we get only one peak. Similarly, in case of acetone, okay, these hydrogens are identical, all are identical homotopic, so we get only one peak, okay? This is just one peak. So this was rotation. The next one is enantiotopic groups. Now enantiotopic groups can be distinguished by systems that can tell right from left but are still magnetically equivalent and appear identical in NMR spectrum. So in this case the products that will be formed, जो products बनेंगे वो थोड़े different होंगे, but इनका जो NMR spectrum में जो हमें signal मिलता है वो same होता है, ठीक है? ऐसा देखते हैं क्योंकि ये भी आइडेंटिकल ही है बट इनका एडिशन या सब्स्टिट्यूशन प्रोडक्ट थोड़ा डिफरेंट होता है, ठीक है? सो द फर्स्ट एग्जांपल यू कैन सी दीज हाइड्रोजन्स इन ब्लैक एंड इन ग्रीन, okay? The first one is the substitution criteria. Two homomorphic ligands are enantiotopic if substitution of one and other by different test ligand leads to enantiomers. So as you can see in example number 2, example 2 में देख सकते हो यहाँ पे HA और HB है, ठीक है? दो हाइड्रोजन है. This is Fisher projection. When you substitute HA by Br, okay, the red hydrogen by Br, you get a product like this, okay? And when you try to find out the configuration of this molecule, okay, so bromine gets priority number 1, the COH groups gets priority number 2 because of C double bond O, and H is the least priority. So when you go clockwise, okay, so that comes out to be R, but since the fourth priority group is present on the horizontal line, the configuration becomes S, okay? So similarly when you substitute HB bromine, okay, so the rotation is in anti-clockwise direction and the configuration comes out to be R because H is present on the horizontal side. Now the third example, as you can see there are two hydrogens, okay, in the middle, okay? When you, and these hydrogens are different actually, one is present above the plane of paper and one is below the plane of paper. So when you replace these hydrogens by something else, okay, say D, okay, when you replace HD, it goes, okay, out of the plane, matlab on the back side, okay? And when you substitute D, there's a different product. So these are enantiomers of each other, okay, and the groups HA and HB are called enantiotopic. Now when you have two atoms, okay, whether you want to know they are enantiotopic or not, when you perform a substitution reaction, okay, the products that are formed are not identical, okay? In homotopic में क्या था, जो प्रोडक्ट बन रहा था वो आइडेंटिकल था, लेकिन enantiotopic में जो प्रोडक्ट बनेगा वो आइडेंटिकल नहीं है, they are enantiomers, okay? So enantiomers बनते हैं तो we call them enantiotopic groups or atoms. Now you can see dichloromethane, okay, right? We are going through the example again. This is one more example. Now as you can see, when we substitute by D, okay, we get these products are basically same, because you see the once you can keep D out of plane and in plane, okay, but the product remains the same. There is a chlorine atom on the side, okay? So basically if you turn around, if you rotate the molecule, these can be interchanged. It would make no difference to anything. So these are homotopic. So we discuss this example again. But what happens in enantiotopic, when there is a substitution reaction, there is formation of enantiomers. One will have an R configuration, one will have an S configuration, okay? Now, okay, two faces of a pi system or a double bond are enantiotopic. Addition to phase gives enantiotopic product. For example, there is a say there is a ketonic group or carbonyl group. Okay, so when you add a ligand or a atom or a group, what happens is there is formation of enantiomeric product. So one important term, एक important term जो हमें learn करनी है वो प्रोस्टीरियो आइसोमेरिज्म है या प्रोकायरलिटी है. प्रोकायरलिटी क्या होता है? ऐसा कार्बन एटम जो कि अगर उस पर एक हम एटम को ऐड कर दे या सब्स्टिट्यूट कर दे, ठीक है, जो कि एक स्टेप में एक रिएक्शन में जो कायरल बन जाए, जो कार्बन, जैसे कोई कायरल कार्बन होता है उस पर 4 डिफरेंट ग्रुप्स अटैच होते हैं. अगर उसमें मान लीजिए कि 2 अलग है और 2 सेम है, और उसमें से जो 2 सेम है उसमें से हम एक को हटा के एक दूसरा लगा दे तो फिर वो कार्बन कायरल बन जाता है. सो दिस इज़ नोन एज प्रोकायरलिटी. मतलब जैसे प्रो चॉइस और इस तरह से हम बात करते हैं, तो वैसे ही प्रोकायरलिटी जो कायरलिटी के फेवर में हो. ओके, नाउ as you can see in the 6th example, you can see this carbonyl group. Okay, there are 2 different groups attached, phenyl and hydrogen, above and below the plane. Okay, so when there is an addition from the upper phase, okay, upper phase red, okay, you know, when you react it with Grignard's reagent, there is addition of ethene ethyl molecule. Okay, so this is R. Okay, the configuration is R, right? And when you do addition from the bottom phase, okay, when there is an attack of the nucleophile from the bottom phase, okay, what happens? There is formation of S. Okay, so the upper phase is pro R, upper phase is pro R and lower phase is pro S. Okay, R for rectus and S for sinister. So the upper phase is pro R, we call it pro R, the upper phase. Now come to example number 7, a very similar example. Okay, here we react it with HCN. Okay, so when there is an attack from the top phase, we get an S, and there is an attack from a bottom phase, we get R. So this is addition of HCN, right? So the next one is the symmetry criteria. Okay, now 2 homomorphic ligands are enantiotopic if they can can be interchanged through a plane of symmetry or center of axis. So how do we decide when you have a plane of symmetry? So that is an important criteria when you have a plane of symmetry and these 2 hydrogen, whether you want to decide if these are enantiotopic or not, right? When there is a plane of symmetry present, that means that these atoms are enantiotopic. Okay, now when this COOH was replaced by some other group, there would be no plane of symmetry and the HA and HB atoms would not be enantiotopic, right? So as you can see in example number 9, what we do is, okay, there is another symmetry that is present, that is sigma H. Okay, sigma H. Now when you pass an axis through the center of the molecule and rotate it and then you reflect, this is the sigma H operation, improper axis symmetry. Okay, when you rotate the molecule and take a reflection, right, you get the, what do you get? What are these 2? Comment down below in example number 9, what do you call these 2? Okay, right? So these are enantiotopic atoms, hydrogen atoms. Now again, when you have an inversion center, then also these chlorine atoms are enantiotopic, or the hydroxy groups are enantiotopic. So this is another example. The next one is diastereotopic groups. Now these diastereotopic groups, what does it mean? Due to these groups, there is a formation of a diastereoisomer, not an enantiomer. So that can also happen. Instead of formation of enantiomer, we can have diastereomer. Okay, Two homomorphic ligands are diastereotopic if the substitution of first one and other by different test ligand are not already attached to the molecule. So let us not get involved in the definition. As you can see, this alkene, okay, we have HA and HB. When you replace any one of the chlorine with any one of the hydrogen atom, okay, इन दोनों hydrogen atom में से किसी को भी chlorine से आप replace करोगे, so what you will get is cis and trans. Okay, now it is with respect to the hydrogen, okay, the cis and trans that we consider is with respect to hydrogen. But what you can actually do is you can assign the EZ configuration also, okay, right? So the number one priority is chlorine on the left hand side, and on the right hand side number one priority is on the left hand side is on methyl group. Okay, so these are trans to each other. So what is the configuration? Okay, E, okay, E, right? So similarly, when HB is replaced by chlorine, we have a cis configuration, okay, both the hydrogens are on the same side, right? Now let us go to the next slide. So this the second example, when you replace any of the H, any of the hydrogen, okay, by chlorine, you will get a cis or a trans again, okay, the same. These are diastereoisomers. Now as you can see in example number 3, okay, there is a stereo center. There is a stereo center, right? On the right hand side there is an ethyl group, methyl group, and this whole thing, okay. So this is a chiral center, and adjacent to this is a carbon, okay. This is also pro-chiral carbon. Just imagine if you replace any one of the hydrogen, this carbon will become chiral, okay. So this is a pro-chiral center. So these are HA and HB. When you replace any one, what will happen? These are usually diastereotopic, okay. Now the fourth example, as you can see, there is a chiral center, okay, chiral center in the star, and there is a carbonyl group. Now addition to this, what will happen? When you add to this, there will be formation of diastereoisomer, okay. I hope that's all right. Then again in the example number 5, you have diastereotopic hydrogens. Due to non-equivalent nature of proton, it splits into multiplet. Now these have different NMR. Enantiotopic atoms had the same NMR, but in case of diastereotopic hydrogens, the NMR spectrum is different. As you can see, all these protons are non-equivalent, okay. These are non-equivalent protons, so the peak is not sharp and single, it splits into a multiplet, okay. Right? The next one, okay. See, this is a chiral center, right? Now when this undergoes addition reaction, we have two diastereoisomers due to sterics, okay. The structure is not like this. Basically it is a 2D structure that we simply draw, but the left one, as it says, the text says, the left one is more favored, but still there is formation of diastereomers, okay. Now in example number 8, when you have a you have this molecule. Okay, so this looks pretty much same, but it's not. Okay, as you can see, the hydrogens in red. Okay, hydrogens in red, and when these undergo substitution by chlorine, we have structures E and F. These are diastereomers, and the two protons are known as diastereotopic. Okay, so I hope that was it for today's lecture. Thank you.